Hello everyone, welcome to my structural analysis tutoring section. I'm Cheng Ning. Today I'm going to talk about how to draw shear force and bending moment diagram. Alright, let's take a look at the question first. Basically, this is a statically determinant structure. It's a beam ABC. The structure is pin supported at A, and roller supported at C, and it is subjected to two downward uniformly distributed loads. And these are the geometry of the structure. And then the first thing you need to realize is that, okay, this, for the first distributed force, the per unit length here for this kind of schematic drawing refers is respect to horizontal distance, okay, horizontal distance. Well, for the second one, okay, the per unit length here is with respect to the slope along the slope. So what I mean is that the total loads produced by the first distributed force is here is 4 kilonewton, and for the second one, the total load produced by this the second distributed force is 2 kilonewtons times 5. 5 basically is the length of BC. 5 meter basically is 10 kilonewton. So the first thing we need to do before we draw the shear force and bending moment diagram is to find out the reaction force. Okay. So how do we find them? We use the equilibrium condition. And so the first equilibrium condition that I've used is a summation of all the moment produced by the external force respect to A is equal to 0. And so this is the moment produced by the first distributed force. The 2 here is the moment arm. And the second term refers to the moment produced by the second distributed force. This is also a moment arm. And the third one is the moment produced by the reaction force Cy. The cosine theta here refers to, okay, let me define theta first. Theta is this one. Okay, this is theta. Cy cosine theta means that the projection of this inclined reaction force projected on the vertical direction. Okay, so in this case cosine theta is 3/5, and this is also the moment arm. Based on this equilibrium condition, you can obtain Cy as 15 kilonewton. Okay, and then from the second equilibrium condition, summation of all the forces along the horizontal directions should be equal to 0, and this is Ax. Okay, and then Cy sine theta again is the projection of this inclined loads on the horizontal direction. In this case, sine theta should be 4/5. So from this equation, you can obtain Ax is equal to negative 12 kilonewton. Negative here means that our assumption of the loading, the direction of the loading, should be reversed. Okay, so what I mean is that this is equivalently, okay, Ax should be equal to 12 kilonewton to a left, okay, towards left. Okay, and from the third equilibrium condition, summation of all the forces acting on the structures along the vertical directions should be equal to 0. So we will obtain that Ay minus this one, this is the first distributed loads, second distributed loads, and also this is the reaction force, the projection of the reaction force. You will find out that Ay is equal to 5 kilonewton. Alright, after we find out all the reaction force, the next thing we need to do before we draw the shear force and bending moment diagram is to do some sort of checking. Okay, to check what? To check the whether we calculate the reaction force correctly or not. Okay, checking. We always need to do. This is I always do checking before I move on. Spend some time here. Okay, to avoid mistakes and checking. For example, I will take summation m, summation of all the moment respect to point C should be equal to 0. So for this one, okay, let's do it together. 10 kilonewton multiplied by the moment arm is 1.5 meter. Basically, this is the moment produced by the second distributed force plus 4 kilonewton, and then this is 3 plus 2. Okay, this is the moment produced by the first distributed force. Distributed force. Okay, and then minus AY multiplied by the moment arm is 7 equal to 0. After some calculation, you should the answer you get should be AY is equal to 5 kilonewton, which is same as our calculation before. So okay, alright, it means that basically we do not make big mistakes, okay, at the beginning. Based on my experience, students always make mistakes in the equilibrium condition, okay, in finding out the reaction force. So this, and then the rest, whatever they did for the rest of the questions, it's not correct. It's not correct. So you better spend some time at the beginning to do some checking to avoid mistake at the beginning. So the next thing you need to do for this question is to do some sort of pre-processing. What I mean is that, okay, for example, for the first distributed load, right, for the first distributed loads, you need to transform it to this kind of format. You need to transform this from this. Okay, why? Because when we draw the shear force diagram, we need to do the integration of the loadings. The loadings here refers to the loading along the slope. Okay, along the slope. What I mean is that if after you do this transformation, you need to decompose it, right? You need to decompose it to this direction. You need to find out the loading here in order to draw the shear force diagram. Okay, remember that when we tackle the horizontal beam, okay, this is loading, right? The loading here actually is along the beam, and also the direction here is transverse with respect to the beam. So we need to again, because our beam is this kind of orientation, right? It's aligned in this kind of orientation. So you need to transform this format to this format, and then further decompose it to this loading and also this loading. So how do we do this? This is pretty straightforward. This is 1 kilonewton per meter, and then the horizontal length is 4 meter. So the total load is 4 kilonewton. We know that this direction from the geometry is 4 square root of 2. So if I want to find out the equivalent loads, basically is like something like this, okay? And omega prime is equal to 1 over square root of 2. The unit is kilonewton per meter. So, but it is not the end of the story. We need to further decompose the loads into two directions, okay? Two perpendicular directions, okay? The loadings, one is along the slope and the other one is transverse to the slope, okay? Perpendicular to the slope. So how do we do this? It's quite straightforward. Let me try to do this here. This is omega prime. We want to decompose to this direction and this direction. This is 45 degrees from the geometry, and so this is basically omega prime cosine 45 degree, basically is 1/2. Okay, so what I mean is that the magnitude of this uniform loads perpendicular to the slope to the beam AB is 1/2. This is the unit. Okay, similarly for this one. By the way, don't forget to do the projection for the second loading. Okay, the second loading is something like this. Okay, the second loading is what is it? The second loading, the second distributed loading is something like this, okay. The magnitude is 2 kilonewton per meter, and then you need to transform this to this and this. This is theta, this is 2, right? This is 2 cosine theta. Basically, is equal to 2 multiplied by 3 over 5 is equal to 6 over 5. And similarly, this is 8 over 5. Okay? But you still cannot start. Okay? You still need one more step before you can draw the shear force and bending moment diagram. You need to further, okay, transform this 2 loading into this 2 loading. The reason is because, okay, you want to draw the shear force diagram, right? You need to find out the first point. You need to jump, right, the shear force. So you need to find out AY prime. AY prime. AY prime basically is a linear combination of AX and AY. In this case, let's try to do this together. This is this is 45 degree, and then this is also 45 degree. This is also 45 degree. So AY prime basically is equal to AY cosine 45 degree, and then minus AX sine 45 degree. Recall that AY is 5 kilonewton and AX is a negative 12 kilonewton. So the total loading for the AY prime is 17 over square root of 2. So we are almost there. We are ready to draw the shear force and bending moment diagram. Alright, let's start to draw the shear force and bending moment diagram. Okay. Let's draw it on the left one. This is shear force. I like to put the units here so that I don't need to write down the units all the way along the structures. It's cleaner. Okay, it's cleaner. So how do we draw the shear force diagram? First of all, we know that there is a jump here. This is 17 over square root of 2, and then we know that the downward, the uniformly distributed force that perpendicular to slope is 1/2. It's here. Where's my pen? Okay, where's my pen? My pen is here. And so this shear force diagram should be something like this. Okay. Let me draw it larger. Decreasing with a rate of 1/2 kilonewton per meter. So the length of this is 4 square root of 2, so it should be 13 square root of 2. Okay. What if I ask you to describe the function of this shear force diagram? How will you do this? Okay, I like to use local coordinates. Okay, let's define this as x1, and then so the shear force of this beam is the starting point is for 17 over square root of 2, and then minus the integration of the loading. So the loading is a constant, so it's 1/2 multiplied by x1. You need to know that the range of x1 is from 0 to 4 square root of 2. Similarly, for this one, the jump here, remember that our cy is 15, and then the loading is this one. Okay, the loading is here. Okay, 6 over 5. So we need to draw it's decreasing, so must be some kind of value that's smaller than this value. So the rate is 6 over 5. Okay, so this is 5, so 6, so this is 9. If I want to describe the function of this shear force diagram, let's define this as a local coordinate. Okay, the function of this shear force diagram is equal to the starting point is 15, and then minus 6 over 5 x. 2. Okay, bear in mind that the range of x2 is only applicable from 0 to 5. So the last but not least is our bending moment diagram. Okay, kilonewton meter. I like to plot it at tensile side. Plot at tensile side. Because I'm a civil engineer. Civil engineer likes, in practice, we like to plot our bending moment at the tensile side so that the workers can locate the reinforcement easily. But it is for practical purposes, okay? So the bending should be like this. Where is my pen? Should be like this. Oops, it's too big. Never mind. Okay, and the value here, right, is the integration of the area of this shear force diagram. But based on my calculation, it's 60. Okay, it's 60. Okay, but if I want to describe this bending moment, mx1 actually is equal to the starting point is 0. Okay, plus the integration of this, the integration of shear force diagram, basically is 17 over square root of 2 minus 1/4 x1 squared. Okay, sorry, this is x, there should be x1 here. Okay, and if you plug in x1 equals to 4 square root of 2, 4 square root of 2, you should get 60, positive 60. You can see that the bending moment is increasing, but the rate of increasing is quite is lower, and because our shear force diagram is decreasing. Okay, of course they are still positive, but the rate of increasing is reduced. Similarly, for the second bending moment here, okay, it should be something like this. Yeah, it should be something like this. The value here should be also let's redraw it again. It's very ugly. Okay, the value here should be also 60. Y is 60. You can try to calculate the area under the curve of shear force diagram. 6 plus 9 plus 15 multiplied by the length of BC divided by 2. Okay, so this is here. But if I want to describe the function of this bending moment diagram, basically is mx2 is equal to the starting point is 0 and then plus the integration of this function. Okay, basically it's 15x x2 minus 3 over 5 x2 squared. Alright, thanks for your watching, and if you like my video, feel free to press the like buttons and subscribe my channel. Thank you.